Okay. So, in this lecture I will basically talk about this distribution substation service area, different types of service area, and will show you that derivation of a generalized expressions for voltage drop. Okay. So, if you can follow my last lecture, I discussed this how to determine these expressions for voltage drop and power loss for typical two types of feeders. One is feeder with a uniformly distributed load with a service area with a rectangular service area. Another example was similar to that this uniformly a feeder with uniformly loaded, but its service area is of triangular. Okay. In both the examples we determine the expressions for power loss and this voltage drop. Okay. Now, in this lecture we will learn the different types of substation service area and in fact, their comparison in view of this voltage drop calculation. Okay. So, let us start with this distributions two different cases. As we know, the distribution substation service area, it means that the area which a substation serves, okay, or area under a particular substation. So, we call it substation service area. It can be of different shape, it can be of different shape, it can be either of square, it can be of circular, it can be of hexagonal, or it can be of any shape. Okay. But here we will try to understand two different shapes for this service area under a particular substation. One is square service area, that is this example, another is hexagonal service area, that is this example, and we will try to compare the feeders of both the types. Okay. We will try to compare the performance or the voltage drop expressions for both the feeders. Okay. Now, look at this example here. This is the point where the substation is located, it is point A. Similarly, in this example the substation is located at the center of the service area, which is named as point A. So, here we have some assumption. The first assumption is that substation is located at the center of the service area. So, all this analysis is based upon this assumption, okay. And we have another 2-3 assumptions also, which I will let you know afterwards. Okay. So, the first assumption is the substation is located at the center of the service area. So, this is a square shaped service area, this is a square shaped service area, as you can see shown over this dotted line, and we assume that substation is located at the center of the square. Okay. Similarly, this is a case of hexagonal service area like this. This is a hexagonal service area where a substation is located at the center of the hexagon. Okay. So, this is the assumption that we took, and all this analysis is based upon this assumption that substation is centrally located, okay, which may not be true for many practical substations or many practical distribution systems, but in this analysis we assume that the substation is centrally located. Okay. And second assumption is that the load distribution is uniform, load distribution is uniform. Okay. So, this is the second assumption. So, load distribution is uniform over the service area, over the entire service area of the substation, over the entire service area of the substation. Okay. So, these are the two assumptions. Based upon these two assumptions, we will analyze the performance of this two different types of feeders. One is located in a square shaped service area, another is located in a hexagonal shaped service area. Okay. Now, here our substation are located at the center, and this is one of the feeder is shown, or this is one of the feeders is shown, and this is the main feeder. This is the main feeder, which is marked over this arrow. This is the main feeder. Okay. And this main feeder is associated with several lateral feeders, as you know. This main feeders is associated with several lateral feeders like this, and these black dots, they are representing the nodes or loading points from where this load is connected. And this is basically, you know, for primary distribution feeder, this is the location of the distribution transformer. This is the location of the distribution transformer, which transforms the voltage level to the utilization voltage level, from primary distribution feeder voltage level to the utilization voltage level, and they are directly connected to the loads. Okay. So, these all are connected to this you know, primary feeders, and some few are shown over here, but this load distribution is uniform, as I have shown you. This is our assumptions. Okay. And this, you know, whatever is connected to the main feeder, this all vertical lines, they represent you know, this lateral feeder, they represent lateral feeder, they represent lateral feeders or simply laterals. Okay. We call it them laterals, and these dots, they represent this load nodes, okay, where we have this loads are connected, okay, where we have this distribution transformer, beyond which we have the customer's load. Okay. And for a typical lateral, as shown over this rectangle, it is the service area of this particular lateral. Similarly, we have many laterals along with this main feeder, which constitute a triangular shaped service area under this feeder. So, if you look at this example, you can see that service area under this particular feeder is of a triangle. Okay. Similarly, this is one particular feeder is shown over here. So, similarly, we have another 3 feeders, which they are, each of this feeder is coming out from the substation like this, from the substation, and they are associated with many such laterals, and for each of the feeders, service area is of triangle. So, for example, for this is one feeder, and this service area is that service area under this particular feeder. So, in total we have 4 number of feeders for this example, and if we can name these feeders as F 1, F 2, F 3 and F 4. So, each of them are marked with this red line, main feeders are marked with red line, and you can understand that for each of the feeder, the service area is a triangle. So, we have 4 triangles here, which constitute a square service area under this particular substation, which constitutes a square service area under this particular substation. Okay. Similarly, for hexagonal service area under a particular substation, this is the main feeder and these are the laterals, this is one feeder is shown, and here also you can see the service area under this particular feeder is of triangle. So, service area under a particular feeder is triangular. Similarly, we have many other we have 5 another feeders, one is this, another is this. So, I am just showing you here these main feeders, but these main feeders of course are associated with some laterals. So, this is suppose F 1, that is main feeder 1, this is F 2, this is F 3, this is F 4 and this is F 5 and this is F 6. So, for each of the feeders this service area under this feeder is of a triangular, and each feeder is associated with many such laterals, and load distribution for each feeder is assumed to be uniform. So, these are the things you have to know before we start this analysis. Okay. And there are some nomenclatures also. I sincerely acknowledge for those nomenclatures for this Turan Gonen's book, which I used as a reference for this lecture. Okay. So, I followed his nomenclature blindly. Okay. Now, this length of each of the feeder is represented by L, and this suffix 4 says that it is the length of the feeder having 4 number of feeders. Okay. Each of the feeders having same length. For example, here you can see this length and that length, this length and that length, all are equal and they are assumed to be L 4. Now, what this suffix 4 is representing? This suffix 4 is representing that it is a case of substation where we have 4 number of feeders and they are connected in a square service area. Okay. Similarly, here also this length of the feeder means it is the distance between the substation and the distant customer of the main feeder. So, it is the length of the main feeder, this is the length of the main feeder, and it is considered to be L 6. This L 6 is representing, again L is the length of the feeder in either in kilometer or in mile or in meter, whatever you can say, and this 6 represent, this suffix 6 represents that it is associated with 6 number of feeders which are connected in a hexagonal service area. Okay. Which are connected in a hexagonal service area, and each of the black dots, they are representing the position of the distribution transformer, as I said, beyond which we have the customers. And what is the role of the distribution transformer? Just to convert or just to step down this voltage level of primary feeder voltage level to utilization voltage level. In India, as you know, primary feeder voltage level, if it is 11 kV, then utilization voltage level 3 phase is around 400 volt. So, these distribution transformers, they are for step down from 11 kV to 400 volt. Okay. Now, let us find out a generalized expression for voltage drop for this kind of feeders. Okay. Now, here we assume that we have a substation service area with n primary feeders, Okay. We have a substation which is serving n primary feeders. Okay. And this is the location of the substation, and one typical feeder is shown over here. So, this is basically representing one typical feeder, Okay. And this length of the feeder is Ln. Here again n stands for this length of nth feeder or length of the feeder which is associated with n number of feeders in a service area of a typical substation. Here also we assume that the substation is centrally located. So, one particular feeder is shown over here. If you look at this previous case, so only one particular, for example, this one is shown in the next slide. Okay. So, this is the point where substation is located. This is the main feeder which is shown over here, that is A B is representing main feeder or trunk feeder, whatever you can call, and its length is Ln either kilometer or mile. Okay. And this BC is basically representing a lateral feeders. Similarly, we have many laterals, not only one laterals. Here also we have these two assumptions valid. One is substation is centrally located and load distribution over the entire service area of this feeder is uniform. Okay. Now, if we put this point as D, then the service area under this feeder is this ACD. So, ACD is basically representing the service area under nth feeder. Okay. So, we have a substation having n number of feeders, substation is centrally located, load distribution is assumed to be uniform, and one particular feeder, that is the nth feeder, is shown over here. Its service area is the area under this triangle ACD, A, C and D. Okay. Now, what we will do, the length of the feeder is also ln given. Now, what we will do here is that at a distance x from the substation, we will take a infinitely small area. We will take a infinitely small area which represents dA. dA is a infinitely small area. Okay. And this angle, that means this CAB, this angle is theta as is given, and of course, by symmetry that angle, that is DAB, will be also theta. Okay. So, which constitutes the total angle, this DAC as 2 theta. Okay. And since it is nth feeder, we have n minus 1 other feeders, and each of having maybe this 2 theta angle. Okay. All right. Now, we have, as we said, n number of primary feeders under this substation. Substation is located at point A, and as we have shown you, this service area is uniformly distributed load. That means, load is uniformly distributed under the service area of this particular feeder, as well as all the other feeders under this particular substation. So, each of the feeder is serving an area of a triangular shape. So, here as I said, this triangle is representing ACD, is representing the service area under this particular feeder. Okay. So, since we have taken this a small elementary length of dx to constitute this infinitely small area dA. So, let us find out the expression of dA in terms of dx. Okay. So, let us assume that this height of this distance is y. So, obviously, this distance will be also y, which constitute this length from here to here, this length is 2 y. So, this length will be of 2 y. Okay. And this length is dx. So, this length is dx. Now, although this is of a trapezoidal shape, but since it is a infinitely small, let us assume that it is a rectangular shape. So, this dA can be written as in terms of this y and dx. So, dA can be written as, where dA can be written as 2 y dx. So, this is the expression for infinitely small service area, which is located x distance away from the substation. Substation is located at point A, and this infinitely small service area of this feeder is located x distance away from the substation. So, here we have this length of the primary feeder is dx. So, we determine this dA in terms of x and y, that is dA is equal to 2 y dx. So, this is not exactly, but it is approximately true, assuming that this infinitely small service area is of rectangular shape. Okay. Now, what would be the load that is served by this infinitely small service area? So, this will be of course, this area dA multiplied by this load density, and load density is assumed to be capital D. Load density is assumed to be capital D. So, the load which is served by this particular area will be equal to. So, this load is represented with a symbol S, capital S. Okay. So, this ds is basically representing load served by this infinitely small surface area, which is equal to load density multiplied by this area, because load density it is a in order of its unit is let us for distribution network is typically a kilowatt per kilometer square or kilowatt per mile square. So, if you multiply it with kilometer square of this area or mile square of the area, so it will give you that much of kilowatt served by that particular area. So, this ds d if you multiply it with dA, then whatever you will be getting, that will be basically the load which is served by the small elementary length, infinitely small elementary length. Okay. So, here our S is basically representing S is symbol S is representing load served. Okay. Now, we have some sort of more analysis. So, since this angle is theta, so if this is d already we have considered. So, if we consider this point is E and this point is F, then this y by x plus dx, x plus dx is dot is by mistakenly it is given is equal to tan theta. So, tan theta is equal to y by this length that is x plus dx. So, y is written in terms of x as y is equal to x plus dx tan theta. Now, as I have said this this area is of infinitely small. So, dx is infinitely small length. So, it is close to 0. So, approximately y can be written as x tan theta just by considering dx is approximately 0. Okay. So, therefore, area of this infinitely small surface area is given as dA 2 y dx, which we got from this last slide, this one dA is equal to 2 y dx. So, if we replace this y with this expression like x tan theta, so dA will come out to be 2 x tan theta. Okay. So, dA will come out to be 2 x tan theta. Now, if we integrate this dA for the entire length of the feeder with a limits of 0 to ln, where ln is representing the entire length of the feeder. So, if we vary this x from 0, 0 is the point where substation is located and ln is the point where extreme end customers of the primary feeder or main feeder is located, that is point B. So, if you integrate on this particular limit, so what we will get this you will get A n, which is basically the area under this particular feeder. So, this A n is basically representing you the area under this particular feeder, that is the area under this triangular surface area of that particular feeder, which constitute this triangle ADC. Okay. So, its expression is coming out to be ln square tan theta. Okay. Where theta is that angle, ln is basically the length of the feeder. Okay. Ln is the length of the feeder. Now, if we multiply this particular surface area, if you multiply it with this particular surface area with load density, then whatever we will get, that will be the load served by that particular feeder. So, here Sn is basically representing load served by the nth feeder. So, whatever Sn will give, that is basically the load served by this nth feeder. Okay. So, that will be load served by nth feeder. Now, we will try to determine the voltage drop of this particular feeder. Okay. Voltage drop of this particular main feeder. Okay. So, this voltage drop expression, as you can see in my previous lecture, this voltage drop expression typically depends upon some parameters. One is Is, one is Z another is L. Okay. Now, the small z is basically the impedance of the feeder per unit length, okay, and it is normally fixed for a particular type of feeder configuration. Okay. L is basically length of the feeder, L is length of the feeder, this z is impedance per unit length, and this I basically representing load current, load current. So, thereby this voltage drop expression we can consider that voltage drop, it is function of, since as I have shown you this z is almost constant, we ignore it, 2/3 is of course constant, it will vary from different service areas, one service area to another service areas. So, 2/3 and z if you ignore, then basically this voltage drop typically vary, it is a typically function of this load, and load is represented by load current as I have mentioned at the very beginning, and this length of the feeder, length of the feeder. So, voltage drop is typically function of load and the length of the feeder. So, with this we will try to determine the expressions for voltage drop of the nth feeder, the voltage drop of the main feeder of the nth feeder under a particular substation which is serving n number of feeders. Okay. So, this VDN is again stands for the voltage drop of the main feeder of the nth feeder under a particular substation. So, this VDN we can understand that it is proportional to this load, function of load multiplied by load and also this length. Okay. So, this function is as you know that it is simply nothing but it is proportional to load multiplied by length. Okay. Okay. Now, this load, let us represent that this load is Sn, okay, and this length of the feeder is Ln. Okay. The load is Sn and length of this Ln. So, Vdn is proportional to Ln multiplied by Sn. Now, since this service area is of triangular, so we know the effective length of the feeder to compute this voltage drop will be 2/3 of the actual length. So, we can write this Vdn is proportional to 2/3 of Ln multiplied by this load demand, and load demand can be either represented, as I said, either load can be either represented by the load current or the load power consumption. So, here we consider this consumption is Sn. Okay. Sn is basically the volt ampere consumption of the load. So, Vdn is proportional to 2/3 Ln, it is the effective length, and this Sn is basically representing this load, okay, in kVA, in kilovolt ampere. Okay. Now, if we just remove this proportional symbol with a proportionality factor k, then this we can get the expression for this voltage drop as 2/3 Ln multiplied by k multiplied by Sn, which is the load served by nth feeder. Okay. So, 2/3 Ln is basically representing the effective length of the feeder, k is representing the proportionality constant or a constant parameter, and this Sn is basically representing the load served by that nth feeder. Okay. Now, as we know that this expression of Sn already we determined from this expression, if we put it over here. So, this we will get Ln square tan theta, and this Ln is multiplied with Ln square. So, this will give you Ln cube, and d will come obviously because of this Sn, and this k is the parameter constant or constant parameter, and this tan theta is comes because of this Sn, okay, because of these expressions. Okay. So, once you get that, this will basically represent a generalized form of the expression for voltage drop. Now, this is voltage drop up to what? This is the voltage drop of a primary feeder. This is the voltage drop of the primary feeder. This is not the maximum voltage drop, but this is typically voltage drop of the main feeder. Okay. Now, this could be maximum voltage drop, I will come to that later on. Now, then what would be the unit for this constant k, because this it is the proportionality constant which is representing the ratio of this voltage drop to the multiplication of length and this load. Okay. So, its unit will be of course, this percentage voltage drop per kVA ampere kilovolt ampere, that is per kVA kilometer. So, its unit will be of course, k its since it is equal to VDN divided by 2/3 of ln, that is effective length, multiplied by Sn. So, this VDN let us represent it with percentage voltage drop, percentage Vd, and this ln is represented, it is either can be represented by kilometer or mile. So, let us represent it by kilometer multiplied by this kVA. kVA is the unit of the load. So, its unit is percentage voltage drop per kilometer kVA or percentage voltage drop per kVA kilometer, both are same. Okay. Now, only one thing we will do, that is we can replace this theta with some as a function of n. How can we do that? If you go back and see this figure. So, this angle is 2 theta, and as I said we have another n minus 1 number of feeders, each of them having 2 theta angle like this. So, overall this 2 theta multiplied by n, which is sum of 2 theta multiplied by 2 theta plus n minus 1 multiplied by 2 theta. So, this is basically giving you n multiplied by 2 theta, which is equal to 360 degree. Okay. So, this gives you theta equal to 360 degree divided by 2 n. Okay. 360 degree divided by 2 n. So, we will replace this theta with this 360 degree by 2 n, and we will get a generalized expressions for voltage drop up to the end of this main feeder, up to the end of this main feeder. But provided this expression is valid for number of feeders more than equal to 3, and these primary feeders are linear in the sense that load distribution is uniform. Okay. So, this equation is constant with total number of feeders greater than equal to 3, and these primary feeders are of linear in the sense that load distribution of the feeder is uniform. Okay. Now, we will be having some case studies, we will be having some case studies. Let us first consider what will happen this voltage drop expression when n is equal to 1. When n is equal to 1, the previous expression is not applicable. Now, what could happen when you are having a single feeder system? In single feeder system, either we may have this rectangular service area, or we may have a square service area, or we may have a triangular service area. Now, if we have a square service area like this, whose this is the main feeder and this is the service area. Okay. So, this length of the main feeder is L1, here again 1 stands for this substation is associated only one feeders, this substation is associated with only one feeder, which is having square service area, square service area. So, if it is true, then this length will be also L1. So, this A1 will be equal to L1 cube, and other assumptions are valid. Only thing is that substation is not centrally located, because only one feeder we have. So, substation is not centrally located here, rather substation is located at the extreme end of that service area, and this feeder length is L1. So, of course, A1 will be equal to L1 square, because it is of a square service area, and because of this type of service area, effective length of the feeder to compute this voltage drop is. So, L effective is basically equal to L 1 by 2. So, this one already we determined in previous day's lecture. So, if you multiply this L 1 by 2 with this A 1 and this capital D is basically this load density. So, total load served by this will be equal to S 1 is equal to D multiplied by L 1 square. So, this is basically S 1. Now, if you multiply this S 1 with L effective and the parameter k is there, then you will get the overall expressions for V d 1. So, V d 1 is nothing but as you have shown this L effective multiplied. So, constant k is equal there k multiplied by L effective multiplied by S 1. So, if you put this expression for L effective as half of this L 1 and S 1 expression is D, where capital D you know its load density and L 1 is the length of the feeder. So, if you replace them, then you will get this expression. Okay. Similarly, here also we can find out when n is equal to 2. Here also we have a two feeder case where substation is centrally located and the service area of each of the feeders are of square. So, this is the service area of one particular feeder which is having length of L 2 and this is the service area of another feeder which is having length of L 2. Okay. So, in that case A 2 will be that the area served by each of the feeder will be this L 2 square, because this is also assumed to be L 2, because this service area under a particular feeder is assumed to be square. So, A 2 will be L 2 square. So, S 2 which is representing the total load served by each of the feeder is basically D into L 2 square, and since the service area is of square, again this L effective will be equal to L 2 by 2. So, if you put it all this expression over there. So, similar to this previous one, you will get the expression for voltage drop when n is equal to 2. Here substation is centrally located, load distributions are of uniform, these two are primary assumptions, and another assumption is that each of the service area of the distribution feeder is square shape. Okay. Now, we have some comparative study, particularly for two distribution networks. One is having 4 number of feeders, another is having 6 number of feeders. So, 4 feeder network means it is a of a square shaped service area, and 6 feeder networks means it is of a hexagonal shaped service area. Hexagonal shaped service area. Okay. Now, we will be having some comparative study for these two cases. In fact, these two cases which I have shown you first slide today. So, this is one case and this is another case. Okay. So, what would be the comparative performance of both the cases? One is having square shaped service area, another is having hexagonal shaped service area under a distribution substation, and substation is centrally located, load distributions is uniform, both these assumptions will valid. Now, as you can see that if n is equal to 4, you can find out what would be the area served by this each of the feeder. So, each of the feeder will serve a area of L 4 square. So, basically this you can derive from this expression, this as you know A n is equal to L n square tan theta. So, we can find out A 4 is equal to L 4 square tan theta, and as we know theta is equal to 360 degree by 2 n. So, L 4 square tan 360 degree divided by 2 n, 2 n is 4 here. So, 2 multiplied by 4. So, which will give you L 4 square tan 45 degree, which is nothing but 1. So, this is L 4 square. Okay. So, we can find out that A 4 is equal to L 4 square, where this A 4, this suffix 4 represents that this is a feeder, this is basically area under a particular feeder for a substation having 4 number of feeders. Okay. But this area is under a particular feeder, the area which is served by a particular feeder for a substation which is serving 4 feeders. Okay. Now, then what will be the total area served by all these 4 feeders? So, this will be 4 multiplied by A 4, and this is represented by T A 4. T A stands for total area served by a particular substation. So, T A stands for total area served by the substation. Okay. So, this area is the total square shape service area that we are having. So, this is 4 multiplied by L 4 square. Now, similarly, we can also find out how much load served by one particular feeders when we have a square shape service area. So, this is nothing but S 4, already we determined, that is equal to D multiplied by L 4 square. This is nothing but load density multiplied by area. This area is already determined, that is L 4 square. So, we get this how much load in kVA that one particular feeder will serve. Similarly, total kVA served by all these feeders is equal to T S 4. T S stands for total load served by all these 4 feeders, which is equal to 4 multiplied by S 4. This is nothing but 4 multiplied by S 4, which is equal to 4 D L 4 square. Now, this T S 4 is also representing total load that the substation is serving. So, this is basically representing the total load that the substation is serving. Okay. Now, what would be the expression for voltage drop of the main feeder? So, this already we determined that the expression, if you put theta is as 360 degree divided by 2 multiplied by n, then this will be tan 45 degree, and so this expression will be 2 up by 3 k multiplied by d L 4 cube. Okay. Now, here one can understand one thing, that this voltage drop of the main feeder, it depends upon this parameter k, it depends upon the load density, it depends upon also the length of the feeder. So, this voltage drop is function of cubic length of the feeder, So, or if we write in text, so it is length of the feeder cube. So, this is the function. So, basically this voltage drop, it will vary with cubic length of the feeders. So, if your feeder length if you increase, then voltage drop according to this length, it will be cubic value of this particular voltage, it will vary in a cubic form. Okay. And also how to determine this load current in a particular main feeder. So, this you can find out, as we know, this load current is nothing but total kilovolt ampere served by this particular feeder divided by root 3 multiplied by line to line voltage of that particular feeder. So, here V L to L is basically representing line to line voltage of the primary feeder. Okay. Now, if we put this value expression S 4 here, S 4 already we determined in the last slide, that S4 is equal to d L4 square. So, if you replace this S4 over here, so you will get the expression that how much load current the main feeder is carrying. So, this is basically this I4 is basically the load current that the feeder carries. Okay. So, I4 is basically representing the load current that the feeder is carrying or the feeder carries. Now, there is another concept called ampacity limit or thermal limit. So, this ampacity or thermal limit both are basically essentially having the same meaning. It means that every conductor, because you know these distribution feeders, they are basically nothing but they consist of some typical conductors, 3-phase conductors, and each of the conductors in a particular phase they have certain capacity, certain ampere capacity, and that capacity is called the thermal capacity or thermal limit. Sometimes it is also called ampacity limit. So, this maximum current one particular feeder is carrying should not exceed that ampacity limit. That is what one of the constraint of designing a particular feeder. So, what is the objective of determining this I4? I4 is basically representing the load current which is carrying by this particular feeder, and this load current or maximum value of this load current should not exceed the ampacity or thermal limit of that particular feeder, and this ampacity limit is basically depends upon that what type of conductors we are using to build that particular feeder. Okay. It depends upon conductor materials, it depends upon the conductor size, cross sectional size. Now, similar to that, we will also determine that area served by a particular feeder for a 6 feeder distribution networks with a hexagonal service area. Here A6 will be equal to 1 upon root 3 L6 square. Here again you can find out like this, this A6 is basically equal to L6 square multiplied by 10 360 degree divided by 2 n. Here n is equal to 6, this is 2 multiplied by 6. Okay. Now, this will give you L6 square, this will be give you tan 30 degree. So, tan 30 degree we know it is 1 upon root 3. So, that is why this 1 upon root 3 will come. In fact, this all this analysis you can do also geometrically for a particular service area. Okay. So, once you get this area served by a particular feeder, so total area served by all the 6 feeders, that means this is the total service area under the substation for a hexagonal shape service area is equal to 6 multiplied by A6. So, this is nothing but 6 multiplied by A6, which is equal to this 6 root 3 multiplied by L6 square. Similarly, the total load served by one of the feeders, each of the feeder rather is equal to d multiplied by this area of individual feeder. So, this is equal to 1 upon root 3 d L6 square. Similarly, total load or total KVA load served by all the 6 feeders, that is T S 6 is equal to 6 multiplied by S 6. So, this T S 6 is basically equal to 6 multiplied by S 6, okay, which is equal to this. So, this is how we can determine the total load served by this whole substation. So, this is nothing but total load served by whole substation okay. That is basically T S 6. Now, you can also find out that expression for percentage voltage drop for the main feeder, which is nothing but if you put this expression of tan 30 degree there in that previous example, then you will get this expression in the generalized expressions, and also you can find out the maximum load current that one particular main feeder at this feeding point, because since each of the feeder is having a triangular shape. So, maximum load current will occur at here and slowly it will reduce to 0 at the end point or beyond this the last customer of the feeder. So, maximum load current will take place at the substation, and that load current we can determine as this I 6, which is equal to S 6 divided by root 3 V line to line. Now, since if you put this expression of S 6 that we got over here, that S 6 is equal to 1 upon root 3 d L 6 square. So, you will get this root 3 and this root 3 will be multiplied, will give you 3, and this numerator will be equal to d L 6 square. So, this is the maximum load current one feeder is carrying. So, maximum load current that one feeder is carrying. Okay. Now, next we will have two important concepts. One is called thermally limited feeder, another is called voltage drop limited feeders. I will come to that. Now, what is thermally limited feeder? In thermally limited feeder, the loading at any feeder is limited to its thermal capacity or ampacity limit. Okay. So, as I said few moments before that every conductors are having some ampacity limit. So, here the feeders loading is limited up to this ampacity limit. This is one of the constraint I will again discuss when I will talk about power distribution system planning, that this each of the feeders loading maximum loading is limited to the individual ampacity limit. Now, if we have two different types of feeders or two different types of examples, two different types of substation service area, one is your square service area, another is your hexagonal service area, and for both the types these feeders are constructed with same types of conductors, with same material, same size, same construction, then they are obviously would be limited by individual thermal limit. If so, then of course, the maximum current carrying by one particular feeder should be equal to the maximum current carrying by one another feeder which is having different service area. So, here I 4 is representing the maximum current which is carrying by square shape service area, I 6 is basically representing the maximum current carrying by the hexagonal shape service area. Now, if we equate these two, both the equations we obtained in these two examples, one is this I 6, another is this I 4. If we equate these two and if you look at these two expressions, both the expressions they are function of this L 4 D and voltage, where voltage and D, VLL and D are assumed to be same for both the cases. So, this D and this D will be cancelled out, this VLL will be cancelled out, but here we have 3 factor because of that 1 upon root 3 term in the area, and whereas we have root 3 factor. So, this gives the relationship of this length of the individual feeders, which is L 6 by L 4 square. So, this has to be root 3 if we have to hold this condition true. Now, under this case we can also find out the ratio of the total area served by the particular feeder. So, this ratio is T A 6 by T A 4, which is same as the total load served by hexagonal feeder and a feeder with hexagonal service area to the total load served by a feeder with a substation having square shape service area. So, this you can find out simply by putting their individual expressions, and that is coming out to be 3 by 2. So, it means that in the numerator, although it is area, but if you multiply it with capital D from both sides. So, whatever you will get that will the load served by individual feeder of individual types of substation service area. So, here in the this is basically a ratio of load served by a feeder of a substation with hexagonal service area, with n is equal to 6, that number of feeder is equal to 6 to the load served by a feeder, not a feeder, basically this T is representing the total load. This will be total load served by a substation with hexagonal service area, that is n is equal to 6 to the total load served by a substation with square service area that is n is equal to 4. So, if it is the case, then you can see with this 6 feeder, a substation having 6 feeder is carrying of course 1.5 times as much as load of the a substation having 4 feeders. If your loading is limited with the ampacity limit, that is thermal capacity limit. Now, similarly, voltage drop limited feeder means each of the feeder loading is limited to a given value of voltage drop. So, here the loading of each of the feeder is limited to a given value of voltage drop. So, we will specify that you can design a feeder, but that feeder should not have more than let us say 5% of voltage drop. The main feeder should not have more than 5% of voltage drop. So, if under this case voltage drop expressions for both the examples should be equated, and this gives you a relationship with this length of the feeder for n number of 4 number of feeders and 6 number of feeders, and thereby in similar way you will get the total area served by the 6 number of feeders and 4 number of feeders. That means, one is hexagonal service area, another is square service area, and that is coming out to be a factor of 1.25 times. So, that means, when your feeder is limited with its voltage drop, then if we have a hexagonal service area with 6 number of feeders, it will carry 1.25 times, that means only 25% more load as compared to a substation with a square service area having 4 number of feeders. Okay. If they are limited with voltage drop limit. So, this is called VDL feeder. Okay. So, with this I will stop today. Thank you.